Let's use the fundamental theorem of calculus to do some calculations. Let's use it to evaluate some definite integrals. So the first one that we want to deal with is, let's say we are asked to integrate, find a definite integral of x cubed dx from 2 to 4. So first thing is we have to ask ourselves, what is an antiderivative of x cubed? So by our undoing the power rule, it would be x to the 4th over 4. But then we have to plug in the endpoint. So the little notation that we do here is, this notation here is saying that first you plug in 4 in for x, then you plug in 2 for x, and then you subtract the 2, which is exactly, it's an alternative way to write this is f of x, and you evaluate it at b, evaluate it at a, and subtract the 2. So this is a little bit of useful shorthand notation. Very much convention to put it on the right, not on the left. You put it on the left. I think I see some people do it. It looks weird. So let's go ahead and substitute in x is 4. So 4 to the 4th divided by 4. Substitute in x is 2. 2 to the 4th divided by 4. And so this is 64. This is 16 divided by 4 is 4. So our answer here is 60. So that's one example here of a definite integral using the fundamental theorem calculus to calculate out a definite integral. Let's do another one. And let's do the integral for the definite integral from 1 to 3 of x to the minus 3/4 plus 3x to the 5/3. So we need to find an antiderivative of this. Antiderivative of x to the minus 3/4, add 1 to the exponent. Minus 3/4 plus 1 is 1/4. Divide it by that exponent. Plus 3 times x to the 5/3 plus 1 is 8/3. Divide it by that exponent. Divide it by 8/3. And we're going to evaluate this between 3 and 1. So let's simplify this a little bit. Dividing by 1/4 is the same thing as multiplying by 4. Dividing by 8/3 is multiplying by 3/8. So we have 9/8 x to the 8/3 here. Again, we're still plugging in 3 and 1. And so what do we end up here? Plug in x is equal to 3. We get 4 times 3 to the 1/4 plus 9/8 times 3 to the 8/3. And then we subtract 4 times 1 to the 1/4 plus 9/8 times 1 to the 8/3. So here's our final answer. We could say that just equals 1 and that just equals 1. Common thing here, make sure you put parentheses around this entire second term. If we were to write this out, it would be negative this and negative this. People often forget that negative sign in these kinds of calculations. Let's do a trig function or two here. So what would happen if we are asked for the integral from 0 to pi of sine x dx? Well, we know that the antiderivative of sine x is minus cosine x. Take the derivative of minus cosine x, you get sine x. And plug in x is pi and x is 0. And so our answer here is minus cosine pi. And then we should be subtracting cosine of 0 here, but those minus signs are going to cancel out. Cosine of pi is minus 1. Cosine of 0 is 1, and so we have 1 plus 1 is equal to 2. So let's just take a moment here to appreciate something that, if you've never thought of before, I think is kind of interesting thing. So we know that here's kind of what our graph of sine of x looks like. So the integral, the definite integral between 0 and pi of sine x dx is exactly this region under this sine curve. It looks kind of like a semicircle. Don't be fooled. It's not a semicircle. It's a region under a sine curve. The sine is going to keep going like that now. And so the interesting thing to realize is the area over one of these sine curve bumps between 0 and pi the answer is a whole number, which is kind of interesting if you think about it. It's probably as unexpected. You might think that, the area under a sine curve is probably going to have pi in it. That would be a very reasonable guess, but here we see that this area doesn't have any pi's in it. It's just is the whole number 2. Here's a question to think about. Let's continue to riff off of this. Let's say we put in another bump of our sine curve, and now that's going to be a downward bump. So one would think that if we do this, that this region, excuse me, has the same area as this region, but this one comes with a positive sign, this one comes with a negative sign, and so we find a definite integral of sine x dx between 0 and 2 pi. That suggests that our answer should be 0. Well, let's do that calculation. The integral from 0 to 2 pi of sine x dx is the integral of minus cosine x between 2 pi and 0. And so we have minus cosine of 2 pi minus cosine of 0. And we end up with minus 1 plus 1. Sure enough, we get 0. Sure enough, these two humps do exactly cancel each other out. So there's lots of good things we can do here. Our definite integrals are matching our intuition for what's going on here with our pictures. Okay, let's wrap up this video, and let's wrap it up with a pre-class problem. So use the fundamental theorem of calculus, part 1, the part we've talked about, to evaluate this integral. Guess it's ever so slightly different in that having you do something with u's instead of with x's, but I'm sure that should not bother you very much.